Hello everyone, my name is Feruz, and today we wanted to share with you the topic about server partitioning without virtual machines. This topic was supposed to be happening together with my co-presenter from Intel, Antti Kervinen, but for some personal reasons he couldn't join the event. So basically, whatever I'm presenting, I will presenting on behalf of two of us. And all the main project, which is the NRI here that you will see soon, it is not the work of mine only or Antti, it's the community work. So we're gonna just show you what it is, and even though we're presenting two people, but it's the work of the community. So let's start. Normally, in the Kubernetes world, when you have some resources and when you're trying to schedule some pods, for the scheduler, the way that the machine looks like is similar to this. What it means is that for the Kubernetes, it just looks at the node, it knows how many cores you have on the node, and it knows how much of memory it has, and that's it. It's like one box of some resources, and then it does the scheduling based on its logic. But this is very, how to say, simplistic or a little bit naive way of looking at the node. And if we try to zoom in this particular imaginary node, we might see something like this. So if you go a little bit deeper, so now we're not looking only at the numbers, but we're looking at the architecture of the node, so hardware architecture. We might see that we have multi-NUMA node architecture. So we have two physical cores, or like a sockets. Then we have some caches. We have some controllers like memory controller, I/O controller, and then we can see some distances between some cores. For example, if you look at this particular imaginary core, so if imagine that the Kubernetes schedules some application on this core, and this application needs to access to some data that is stored on this memory, which is on the same NUMA node, so this would be considered as a local access. So it's a little bit faster relatively to what? So relatively to going through the interconnect. For example, if the data is stored on the right side, somewhere here, and your pod is using the core from this CPU or this NUMA, then for the access it would have to travel through the interconnect. So the idea is that can we actually take this view of the node and expose it to Kubernetes and then make a little bit better or smarter scheduling. But the topic is not about scheduling. The topic was about partitioning the server. So one of the ways to partition the server was using the virtualization. So you have normally the kernel, then OS, then the hypervisor, and then you divide this big server, for example, imaginary, into small 3 pieces or small virtual machines. But basically, all of these virtual machines are sharing the underlying resources, like the CPU, let's say, and memory, in a simplistic way. Each of them having its own kernel. But there are pros and cons of virtualization. But on the other hand, what we're trying to kind of, let's say, advertise in a way is to use, not to use the virtualization, but directly partition the hardware resources for the Kubernetes workload without using basically virtualization. So what we do is that imagine you have the Kubernetes workload or the Kubernetes that's running on your operating system, on top of operating system. And then can we divide the resources into smaller groups without introducing extra complexity? Yes, we can, and that's the main topic of today. So what is that magic thing that runs on top of Kubernetes that can help us to partition our server without hypervisor? And one more thing, like a disclaimer, we're not trying to compare virtualization versus whatever I'm going to present. It is just that there are different ways of partitioning the machines or the servers. So for understanding how can we partition our server for the Kubernetes workload / for any workload that runs through container runtimes like containerd cryo. So we need one of the main things, which is the NRI. So NRI, which stands for Node Resource Interface, it is the interface that is baked into the container runtimes, both CRI-O and then the containerd. It is container runtime agnostic, meaning no matter which runtime you use, it acts the same way. It is basically sitting on the runtime and trying to intercept the traffic and doing its magic thing with the help of some other components, which are called plugins. So the feature is turned on by default if you're using the containerd version 2. Anything above. For the CRI-O, it's in progress. It's not turned on by default, meaning if you are interested to use NRI and plugins, you have to manually opt in for it. So you have to go and turn on the feature for the CRI-O for now. But there's a work in progress that we're trying to also enable by default. So NRI is an interface, as I said, within the runtimes. It's actually not doing anything, in a way, if you think. So the logic that you need, let's say for our case, to do the partitioning is within the plugins. So the question is, who builds the plugin? Is it the runtime folks, or is it the cluster admin, or somebody else? So there are existing open plugins that people build for different purposes, but if you're not satisfied, or if you have some specific use case, of course you're free to develop your own plugin. Writing plugin is kind of relatively easy than in the past. By in the past, I mean like back in the, compared to the last 2 years. So there is already kind of the skeleton for how to write the plugins, and you could basically, based on that, and then try to create your own custom or like the business logic, let's say. So some of the plugins are listed here. I'm not going to talk through each. I'm not going to describe all of those, but these are some open or publicly available plugins that people have developed. So each one of them has different purpose. So some are purely about resource management, trying to optimize the resource consumption for the Kubernetes. Some are about memory management and the memory QoS. Some about SGX encryption, hook injection, logging, debugging, security, and you can just come up whatever plugin you have in your mind. So those plugins that are here, plus the others, are available under container/NRI plugin repo. This is the first place, or one of the place. And the other one is under containerd GitHub org inside the NRI repository. So we have the NRI. We said it's an interface inside the container runtime, but now we need the actual thing, which is the plugin. So let's see how it works in practice. Imagine you have the physical server that, in a simplistic way, looks like this. So you have 4 cores, 2 L2 caches, each shared between 2 cores, and then L3 cache that is shared across all the cores. Now you have the Kubernetes workload that is running on the same node, let's say, and you have some applications, A, B, and infra pods. NRI plugin is itself also run as a Kubernetes workload. So it's running as a pods, as a daemon set, but then it creates the pods. And it manages the way that your workload ends up on the node. So in our case, again, I'm trying to emphasize that we want to do, in a way, resource optimization, because this is part of this partitioning of the nodes. So how it works in practice is that, let's say the user asks to create a pod A. So normally your pod creation request would go into the kubelet first, which is the node agent. So from the kubelet, then through the CRI interface, container runtime interface, it goes to the high-level container runtimes, like containerd or CRI-O. And NRI is part of the runtime, so you don't technically have to do anything, nor you have to enable it if you're using the latest version. So then containerd is, with the help of NRI interface, it's basically passing or creating the OCI spec and then passing it down to the NRI plugin, which is running on the same cluster. So it says, okay, I have this OCI spec, do whatever you want with the OCI spec, meaning it will go and tune certain fields. So NRI plugin, based on its logic that is written within the plugin, it does some tuning into the OCI spec. Now the modified OCI spec is again passed down to the containerd, and then from containerd it goes down to the crun or any other runtimes. And then from the run C, it goes to the kernel C group creation and so on. So if you don't have the NRI and NRI plugin usage, then you would just skip basically this part. So it would just go flow like this. But in our case, what we are doing with the NRI plugin intercepting the traffic and then modifying its certain fields. So the question is, what did we modify and why are we modifying it? As I said, every plugin has its own purpose, and in our case, again, this is kind of resource usage optimization, let's say. So back to the original scenario. So one of the plugins that I'm going to use today is called Balloons. So what it does is that it is basically creating this isolated, kind of virtually isolated set of CPUs. Every balloon represents a number of the CPU cores, which are isolated from each other. And balloons usually can inflate or deflate. It means, for example, you could create a static balloon or dynamic balloon. Dynamic means if your workload needs more cores, then it can inflate, so it can use more cores. Or if your workload demand in terms of CPU goes down, then the balloon will deflate. So it will just release the CPU cores that are not in use, so that somebody else or some other processes or some other balloons could use it. So that's the idea. So we're going to use the balloons. We'll see how it works, what we can do, and how can we, the most important part is that how can we really partition the server. So apart from partitioning the server with the CPUs, we could partition it in terms of different resources. So you can partition based on the sockets or the dies or the NUMA zones. You can say this balloon represents NUMA zone A. This balloon represents, well, NUMA zone 0, for example, or NUMA zone 1. And then you can say that this is the workload that I want to be isolated in 2 different NUMA zones. Or you could say create the balloons based on different memory types like HBM, DRAM, PMM. Or you could say that create the balloons based on the operating frequencies. Or you can say create the balloons based on kernel isolated features. Like there are some users or like people who are interested in using only kernel isolated CPUs for their workloads. And then you could just create a balloon, say that you would represent only the kernel isolated CPUs, and then you create your workload and attach it to that specific balloon so that nobody else is using those cores, only your, let's say, latency sensitive or latency sensitive workload. Based on the hyperthreading, you can say that use the balloons or create the balloons if there's hyperthreading enabled or disabled, or based on the efficient and the performance cores. So there are different ways that you could create the balloons and then try to kind of differentiate between each other. And then based on that, then you do the workload placement. So, but today's top part is that not about CPU, not about the memory, but more about the caching. So one of the use cases that we have at Ericsson is that some people are interested in isolating their workloads in terms of the caches. And before I talk a little bit about that use case, I just wanted to highlight quickly to show how the caching looks like. You probably know it, but just in case. So there are different levels of the caches, so L1, L2, and L3. L3 is called also LLC. Most of the time it's shared between all the cores. L2 is shared between the cores, between usually 2 cores, but it could be also specific or very close to a particular core. And L1 is very tied to one particular core. So if you look at this diagram or this picture, imagine on the left you have the core, and then on the right side you have different levels of the caches. So usually L1 is the smallest cache, but it's the fastest cache. While on the other hand, L3 is the slowest one, but it's the biggest one. So there's a trade-off. And then the main memory is the slowest among all of these, of course. And there was a talk, I think, in the previous OSS summit that I included a reference, and there was the study where they measured the access time between different caches, and roughly it was, for example, between L2 and 3, it was like 3 to 50 times slower. So now, what is this diagram? So in the demo, at the end of the talk, I have the machine. It's an Intel machine that has 2 NUMA zones, and it has 128. So it has 128 cores, and then, for example, this is one NUMA zone, and this is another NUMA zone. So we have L2 caches, and then we have, for every core, we have L1 caches, and every L2 cache is shared between 2 cores. So why it matters, you will see soon. And the use case is this, but this is again just a simplistic view of the use case because we have limited time. So just imagine that we have 2 sets of workloads. One is the infrastructure pods, and the other one is the application pods. And we want to make sure that, so all of these pods are running on the same node, on a single node. How can we isolate these 2 groups of the nodes so that they do not share the same L2 cache? So, and what we want to do visually, if you want to imagine, is that let's say we have 4 cores that we need for the application pods and 4 cores that we need for the infra. And then there are L2 caches. We basically want to isolate them so that they do not share the caches between each other. So now is the demo time. I hope you have a little bit of understanding where we are going. So we have the NRI, which is part of the runtime. We have the NRI plugin, and in this case, we're going to use the balloons. And we have 2 groups of the workloads that we want to isolate in terms of the caches, basically partition the node. So let's see if it's going to work. I have the recording just in case if there's a demo effect as a plan B. Let me see. All right. So I have a single node, the same machine, 128 cores. Well, let's maybe start from here. 2 NUMA zones, as you can see, 64 instances of L2 caches. So basically, if you do the simple math, I have 128 cores, so 2 cores are sharing the 1 cache, L2 cache, basically. Yeah, and then this is just a simple kubeadm cluster, and if I list the pods, so I have just standard stuff, Prometheus and then NRI. So NRI I have installed, if I do this, so I have balloons policy. This is NRI policy, plugin. So NRI is part of the runtime. I haven't done anything on that front. I just installed the Helm chart of the balloons policy. So when I create these balloons, I have to, it's pretty smart. It has so many knobs that you can control. Like I was showing earlier, how can we partition the node? So different in terms of different resources. So, and because of that, we have too many knobs, which is good and in a way bad, because it might be very complex and you have to be very careful. You just need to know what you're doing, basically. But anyways, in this case, what I did is that I will show you. So the way that we talk to the balloons policy is through the CRD, custom resource definition. And if I list the CRDs that I have in my cluster, it's called balloons policy CRD. So that's the way that I basically talk to the plugin to do anything for me. So there is a default instance of this CR that is created. So you might be wondering, why is it created by default if I didn't ask anything to do, if I didn't ask it? The reason is that the balloon is trying to be smart, and even if you are just starting with the project, or if you don't, if the basic optimization of the balloons policy is enough for you, then you could just, you don't have to do anything, you just install it and that's it. So let's do this. So if you look at the way that it looks, I'm not going to describe all the details because it's very, it takes a lot of time. And I have the same steps later on recorded and then on the GitHub, so you could try it on your own. So I would just ask you just to focus on only particular fields. So this is similar to, I'm just trying to imagine if there's any resource on the Kubernetes. It's like a daemon set in a way that you create multiple replicas of the pods, but the problem, not the problem, but the difference between the daemon set and this balloons types is that in the daemon set, the configuration is the same across all the replicas, but here it's different. So for example, under the balloon types, I can create like basically array of different balloons, like you saw earlier, like red, blue, green, and I could just configure it differently. For example, in this case, I'm creating a balloon named apps, and then I'm saying that, hey, you balloon will be responsible for the pods that are created on the apps namespace. That means if I create a pods on the apps namespace, it will be attached to this balloon, and whatever is told to this balloon, it will do that only for that particular workload. Then the other thing that is interesting, irrelevant for now, is that shared idle CPUs in the same. So this is the interesting part. So what I'm saying here is that whenever there is inflation requested, so whenever there is more cores that are needed for my workload that is running on the apps namespace, so balloons need to inflate, so it needs to take more cores from the system. It can go randomly, but that wouldn't be smart. So it will try to inflate in a way that the same cache is used as the one that is currently used. For example, if I have the workload that is using 1 core, and then I'm trying to inflate it, now it has to take, for example, 2 cores, it will try to take the same core that is shared between the same L2 cache. You can say between the L2 caches, you can say between the NUMA nodes, you can say between the sockets. So there are different levels, basically. And then I'm creating another instance, very similar to this. There's one problem that I see, that the names are names are the same, so I should fix this. Or no, just a moment. It looks very awkward, but okay, this was not supposed to be the apps. This was supposed, let's fix it actually. So the other one is for the infra workload, basically. So we're gonna fix that quickly. And if so this should be the infra port. So the name of the balloon is infra, and it should be taking the pods that are created on the infra namespace, and it should also try to do the L2 caching based inflation. So now if I save it, now the policy is created. 2 balloons with the same apps. Yeah, it actually reported it earlier, but I didn't notice it. Yeah, now it's success, but earlier I had it on the status, which I missed. So now what we do is that we create pods on different namespaces. So let's check the pods first on the infra namespace. So we don't have the pods, and we do the same for the apps namespace. We don't have any pods. So, and then I have, all right. So if we check this simple deployment, it's just creating Nginx on the infra namespace and requesting 1 CPU. So it's a guaranteed pod because the limits and then the requests are the same. And then the other one is the apps. It's the same thing, but the namespace is different if you look. So let's create this. So we created the apps and we create the infra as well. All right. So let's check the pods. So the pod is created, and let's check the other one. Okay. The question is, what did balloon do right now? So we have this. Let me see if I can find it. small utility which is gonna tell us which CPU sets or which CPUs are available for the pods that are running on specific namespace. In this case, it's on the apps. So it's saying that 17 and 81 is available, but it doesn't mean that both of them are used. And I will explain later on why. And if we check the other one, it picked 19 and 33. But this is a little bit confusing because I asked for 1 core, but this script is telling me that it's showing 2 cores because this is it's not because of the scripts issue, but because of this particular pass. But to be correct, I have also the Prometheus enabled here. So we have the Prometheus that is also generating some metrics. What I'm doing is that I'm basically filtering out the balloon types with particular name, if you remember, and then checking which CPU cores are assigned for each balloon and each container. So here it's saying you have the balloon instance that is called apps that has 1 container running that is consuming core number 17, and there is only 1 core, okay? And the other one is the infra part, and it's also using 1. So the question is, now I will inflate it. Basically, I will increase the replicas of my deployment. Then, obviously, balloon will need to inflate. It will need to take 1 more core. But the question is, which core will it take? So the idea was that it should take the core that is sharing the same L2 cache as these 2. So before we inflate, let's make sure that we know which is the core that is shared between the L2 caches between the 17 and 19. For that, we also have just another utility. Well, not the utility, but it's just a shell script. Then I will enter, so the core number here, I will ask 17, and it's going to say, okay, between the 17 number, between the core 17 and 81, L2 cache shared like the ID is 68. And then for the other container, it was 19. So now if I ask for the 19, if I ask for the 19, it's saying between the, so L2 cache that is shared between 19 and 83, it's 82. So now what we're expecting is that now if I inflate, it should use 81 for the apps and then 83 for the infra, if I'm not wrong. So let's do that. kubectl, and we will see it from the Prometheus from here. So kubectl, scale the deployment, nginx in the name apps, and then we're gonna pass the replicas. Now it froze. Okay, into 2, and then we will do the same with the infra namespace. All right. Yeah, the names are the same. So, but let's check that the pods are. Get the pods in the infra namespace. Okay, that's good. And then if we check this one, so we have it. Now, the interesting part is that let's see what the Prometheus is showing. So it takes some time. I have configured for the Prometheus to, well, within the NRI policy, for the metrics to be updated every 15 seconds. So it just takes, okay, we have it. So now what it's saying is that for the apps, it took the 81. And if you remember, 81 and 17 are sharing the same L2 cache. And the other one is 83 between 19, so it's exactly the same cache. So what it means is that I'm using the same cache, or I did the partitioning based on the caches while trying to inflate the workload. So in a way, like now you can be sure that the caches are isolated and they do not interfere. So let's switch back now to the slides. Just a quick recap. So what we were trying to do is that partition the hardware resources, especially for the containerized workloads. So it could be Kubernetes, it could be outside of Kubernetes. As long as you are using runtime, then you should be good, because this is part of the runtime. There is no prerequisite for you to use the Kubernetes. We saw cache-based isolation scenario. That's just one out of, I don't know, 100 or 1,000 scenarios. We saw a little bit about NRI, how it's baked into the runtime, and then we saw, as one example, just one plugin, but there are at least for the time being, I see more than 10 plugins already that are publicly available, and some companies are doing it on their own, as far as I know. So I know that the time is limited, so that probably either you understood some parts of the demo or you did not. But if you want to try exactly the same steps, I have the GitHub repo where I've included all the steps, so you could just try it on your own. And then on the other hand, I would really appreciate your feedback just about the slides or just the way that I present, whether you liked or not. There are max 5 questions that will take less than 5 minutes, and I would really appreciate if you could just share your feedback. So I guess that's the end of the demo, and then now we take some time for the questions. Any questions? Yep, please.
Yeah, what's the kernel functionality behind isolating the caches? Because it usually use C groups.
Yeah. So the question was, what is the technology that is used under the hood to do the cache isolation? So we're not actually isolating the caches here in a way that we don't put the blocker on the Linux kernel. We're just isolating or trying to put the workload far away from each other so that they don't use the same hardware under the hood. But if you want to do the cache partitioning, then there is RDT from Intel. There is an implementation on the kernel called REST controller. So you can use Go REST controller to do the partitioning. And actually, you can do it with the policy, and I can quickly show that. I was planning to include it as well, but it would have been too much for today. So kube system typo. I think it will take it, yeah. And then OYAML. So if you look here, so we have the control and RDT. So if the RDT is supported on your machine, then you can enable this field. So while installing the plugin, you can enable it. And then you can pass the configuration of the partitioning based on the RDT's format. So this is basically, if you look at how the RDT does the partition, it's basically almost the same way that we do. So you can say, okay, for this workload, this percentage of the cache is isolated, for this one, this much. But what I was showing earlier, we're not doing anything on the hardware or on the kernel. We're just isolating workloads from the higher level.
RDT is the hardware enabled.
Yes, that's for the Intel, and I think there is similar for the AMD. I think it's something QoS. I don't recall. Yeah.
Do we have any performance analysis, like when you partition the cache, how it impacts?
That's a good question, and that's my actually task at work that I have to do. But I haven't done it, to be honest. No, not yet. But yeah, I should. At least my manager's asking, so. Any other questions? Yep, please.
What happens after just you set the configure policy, right?
Sorry, could you repeat the question?
So NRI, what it does is just sets the configure policy, like adds containers to configure, right?
Yeah. It's basically, it takes the pod spec and it changes certain directory, like cgroup directories, based on the logic. So in this particular case for the balloons, it basically builds the tree, like it builds a tree of the nodes, so the root, then the sockets, and then the dies, then the numazotes, and then the cores. And then based on your configuration, it tries to optimize the resource utilization, and then when the pod spec comes, based on how the logic works, it just modifies the certain fields for the C group, and that's it. There are limits that you cannot change everything, of course, in the pod spec. There are limits, especially for the security. And if you're also wondering what about security, well, since NRI is part of the container runtimes, then it's part of the runtime, basically. So if you trust runtime, then It's the same security, how to say, like configurations basically.
What kind of workloads have been benefited by this?
So the question is, what kind of workloads have benefit from this? Well, in our case, I know one particular case, which is the cache isolation. There are the noisy neighbor problems, so latency-sensitive workloads that you want to isolate. But mostly what I've heard is about latency optimization, basically. So because you could, instead of going through the interconnect, doing the remote access, you could just try to squeeze in one NUMA zone as much as possible so that it's faster to access the memory. So that's what I've heard. But what we are talking right now is just one part of the NRI and plugins. This is just the resource management. There are like security-related stuff that you can do. There is this hook injections, the logging, and so on. So it's just like one branch. Just imagine that if you are given the whole OCA spec, like there's so many things that you can modify basically. So we're giving access to you to modify the fields or to the plugins, let's say. So you could just come up with different configurations. Yeah.
Maybe, for example, runtime, like Java runtime, if you would run all your Java on one L3 cache.
Well, L3 cache is usually shared between all the cores, right? So maybe if it's L2, let's say, maybe yes, you could isolate, probably. Yeah, please.
Is there a hard limit on the ballooning? So let's say that you want to have share the same level 2 cache,
Yeah.
and you want to have more cores than that are sharing level 2 cache. Will it take up one, or will it just?
Yeah. So this is called. So there are two groups, though. It could be static and dynamic. Static means you could set the hard limits. There's a field called minimum CPUs and the maximum CPUs, for example. So if you set those limits, it will just stick to that. If you don't set, though, it means dynamic. So it could just shrink, like inflate and deflate. It's based on your preferences. Yeah, exactly. I did not include it in the demo, but since there were no numbers, so this was dynamic. So it could go to the whole system, basically 128 cores, if needed.